going to explain Laplace Transform. Sorry. Well, my screen is a little bit too bright, so I'm just going to adjust that. Okay, that looks better. Laplace Transform. Okay, we are going to look at some basics, and we are going to learn how we can apply this transform in order to solve one of the examples that we have done looking at mechanical systems. So a little bit of introduction. So far everything that we discussed and we explored was looking at systems from a time perspective. So when we were looking at a system, and often I describe a system as a black box that we can put on top of a complicated system, and we look at what kind of input or inputs are passed through that system, and what kind of output or outputs are expected from that system. So when we were looking at the inputs, we were looking at time domain or time perspective of that data, and when we were looking at outputs, same, we are looking at in time domain or time dimension or time perspective of that output that we expect from a typical system. So looking at mechanical system, often we were looking at F of t. It was the force that was applied to the system. When we were looking at electrical system, we often look at voltage in time, V of t. Or sometimes we were looking at current, I of t. So you can see that the letter T here is representing time, and we were looking at time dimension or time domain in this story. Now, there is another way of looking at that, another angle, another perspective that we can look at this system, and that is the reason that we can apply Laplace transform in order to make things a little bit more meaningful and considering a little bit more details of what's going on inside the system. So everything from here can be converted to S domain. Someone might ask why we call it S domain. So that S can stand for system, and later on you will see that the parameter S plays a very important role. Sometimes you might hear people saying frequency domain. Okay, this frequency domain is also commonly in use by engineers and designers, and they are looking at the system from similar perspective. Remember, this frequency domain is different from the frequency of oscillation that we were talking about. That frequency comes handy later on when you are looking at how a system oscillation can settle down, and at what frequency a system can settle down. For example, the spring that was oscillating, or a system that was attached to that. So the oscillation here, that can have a frequency, right? That's different discussion. For here, we are looking at finding poles or roots. That's another one, poles or roots. They are very important concepts. That's the whole point. By doing applying Laplace transform, we want to get to the poles or roots. What they are actually the values of S. All right. So value of S is going to sit on exponential of st when we convert it back, and this exponential is referring to the oscillation and settling down the system. So if you remember, when we were looking at responses, we often looked at immediate response of a system, and we were looking at oscillation and settling down response. Okay, so when we are looking at values of s, we want to know how this exponential plot can accurately be plotted. So at what stage the system is settling down. Okay, so that's introduction. Let's take a look at the formula. Okay, so the main formula for Laplace, I'm going to write the formula on top and have the table after that. So I'm just quickly checking about the quality of my recording. Okay, looks good. So Laplace Transform. Okay, we show it with this cursive L and then curly bracket f of t is equal to integral of 0 to infinity of f of t exponential minus st respect to t, right? So what's happening here? We have this integral. It is looking at all the values. It's very interesting because this means that we are looking at initial values. Normally this 0 here is actually looking at a start, which is very important. Often systems do start from 0, but there are times that they don't start from 0. So that might vary the way that we calculate things. Alright? And then this exponential is what I described earlier. So this is looking at the response. Okay, what kind of response we are getting. Okay, we want to figure this out accurately based on what kind of s we're getting. Okay, so what is this? This is the function in time. In time, it can be anything. It can be force, it can be voltage, current, yeah, and so on. So don't worry, it looks a bit complicated, but we don't have to memorize all the integrals. In fact, there is this handy table that we can use, and I'm going to make a nice table here. Hopefully I have enough space. So let's make two tables. So one table here. Alright, so I'm going to have I start from very simple. I'm going to have f of t, different kinds of f of t here, and the conversion after the transform, which is going to basically give us capital F of s, because t is being transformed to s. So one typical example is just 1. Alright, so this 1 is going to be converted to 1 over s. Next simple f of t is t itself, and that will be transformed to 1 over s squared. And we can have t square, and then we can have 2 over s to the power of 3. So as you can see, I can increase that to the t to the power of n, generic form for that. Now let's do one exponential. So if I have e to the power of at, I am going to have 1 over s minus a. So that's a constant a here. And let's do some more examples. I think I have enough space to have some more examples. So if I have derivative, okay, so let's do x of t first. So what is x of t? Looking at mechanical system, that can be displacement. So if I have x of t, I have the s domain version of that as capital X of s. Alright, now very common form of looking at velocity or speed of rate of change of displacement was looking at first derivative. So first derivative, we often look at it as dx over dt. Another way of writing that is by looking at x and putting a dot. That's Newton dot. So we call it x dot. That is referring to the same thing, and you know that this is x of t is respect to t. So this x dot is also x dot of t. Another way of writing that would be using prime. So prime sign here, and then again we are looking at t. They are all referring to the same thing. We are looking at rate of change in respect to time. So I think I'm going to use x dot for this explanation. No, but if you see any of these forms, you know that they are talking about the same thing. So that is going to be transformed to capital S or a small x, capital X of S minus a small x of 0. So someone might ask, what is that? This is the initial value that I mentioned previously, initial value, okay, which is really important for many cases. Now another common equation that you can see has second derivative. So second derivative of x respect to time, we can show that with x double dot. Again, we are looking at time, and also you can have double prime. They are referring to the same thing, okay, second derivative. I am going to use second dot for these examples. So when we have that, result of transform is going to give us s square x of s minus s x of 0. I think I need more space in my table. I'm just going to keep writing, and x dot or prime of 0. Alright, so on top of having the initial value, I also have initial derivative. Alright, so they are looking at the start of a system. The system. Alright, and the last form that I think is useful to know is having integral. So integral from 0 to, let's say, t of f of let's use another parameter here, so whatever comes here, right, I can conclude that as f of s divided by s. Okay, having this table should be good enough to do all the differential equations that we discuss in control automation module. Alright, let's take a look at one of the typical examples that we had. Okay, I'm just double checking my recording and looks good. Alright, so one typical example that we were looking was a system, mechanical system, having all three components: the spring with constant K, the dashboard constant C, attached to a mass with constant N. So the force F is applied for pulling it or pushing it, and the differential equation for this system can be written as f of t is equal to k x plus c, derivative of x in time, and second derivative of x in time. Right, what is that? It's time domain differential equation. Now we want to convert that into Laplace. How we do that? Okay, we apply